Welcome to Analog Electronics. This is lecture 38 and today we will continue from the power amplifiers that we had discussed in the last class. So, in the last class we were discussing class A, class B, class AB, class C power amplifiers. We had just about started our discussion on class D power amplifiers. So, today our agenda is to cover class D amplifiers and then push pull amplifiers, which is another variation of power amplifiers of class B power amplifiers. Okay. So, in the last class what we were doing, so our power amplifier circuit is the same standard one. There is a big inductor for bias purposes. F is a filter, okay, and my input has a bias voltage VGS plus a signal voltage, which is the actual input. And most of the game is in this bias voltage. So, you change the bias voltage, you get to select which class of amplifier you are going to be, whether it is class A, class B or class C or class AB, where you are in the picture depends on this bias voltage. Okay. So, this is what we have studied so far. So, I apply a bias voltage, I apply a signal. If the bias voltage is let us say enough to continuously conduct the MOSFET, then you are in a you are working as a class A amplifier, class A power amplifier, and we saw that the theoretical upper bound of the efficiency of a class A power amplifier is 50%. Okay. So, the capacitor and the inductor are such that you can split the DC bias, the DC current, the DC quantity of the voltage and the current from the signal quantity of the voltage and the current. Okay. And this filter does a further splitting. The signal small I d is filtered by this filter such that only the fundamental component goes into the load, all the other components go through the filter. So, this is the arrangement. Now, what we do is, if I start lowering the bias voltage, then what happens is that the MOSFET is no longer continuously conducting. So, let us draw the picture. So, this is small I sub capital D as a function of time, and so one possibility in class A, the best case scenario is going up and down in this fashion. This is the best case scenario in class A, right. In class B, you cut off the negative half cycle altogether. All right. So, the conduction angle is just 180 degrees. In class C, so let me write this down. So, in between class A and class B, if you are somewhere in between, then what is that going to be called? It is going to be called class AB. Okay. So, that is a conduction angle more than 180 degrees, but less than 360 degrees, that is class AB. Then you have got class B, where the conduction angle is 180 degrees. Then I decrease the conduction angle further, and I get class C. Okay. So, here the conduction angle is less than 180 degrees. All right. And what we did in the last class was we came up with a closed form expression actually. We said that let us say that the conduction angle is 2 times alpha. So, we said let us say this angle is alpha. Okay. So, let us say that the MOSFET is conducting from pi by 2 minus alpha to pi by 2 plus alpha in this region. All right. And we came up with a closed form expression for the maximum efficiency of the power amplifier. And we found that okay, this was the maximum efficiency. For example, if alpha is 0, so I am sorry, if alpha is yeah, am I making a mistake?
So, that is not alpha from here, so from 0 to
okay. So, this is what we had done in the last class. Okay. So, here the conduction angle is actually pi minus 2 alpha is the total conduction angle. So, for example, if alpha is equal to 0, then you are actually boiling down to a class B situation. So, you get pi minus 0. So, pi in the numerator and 2 times cos of alpha, that is 2 minus 0 plus a 0. So, there was a half also. Please check the notes, there was a half also factor in this. So, we had got pi by 4 as the efficiency when the conduction angle is pi, that is it is a class B circuit. Okay. So, this was the situation. And for example, if we now decrease the conduction angle further, let us say I make this alpha a little more, let us say I make alpha equal to pi by 4, then we had worked out pi minus pi by 2 minus sine of pi by 2, that is 1, okay, divided by whatever you have, and overall you will find that the efficiency has increased. Now, what you are also going to notice is that the efficiency has increased, but the actual values of the numerator and the denominator are both decreasing, the actual values. Okay. For example, when alpha has become pi by 4, okay, pi minus 2 alpha, 2 alpha is pi by 2, minus sine 2 alpha, sine of pi by 2 is 1. So, pi minus pi by 2, so that is pi by 2 minus 1. Okay. So, you find that the numerator has become of the order of 0.5, little more than 0.5. Okay. And the denominator, if you look at the denominator now, the denominator has become 2 times cos alpha, cos pi by 4. Okay. So, that is root 2 minus pi sin alpha, pi times root 2, sorry, pi by root 2 plus 2 alpha sin alpha. So, 2 times pi by 4. So, that is pi by 2 times 1 by root 2. Okay. So, if you work this out, this boils down to something a little more than 0.5. Okay. Overall, you will find that the quantity in the numerator has decreased, the quantity in the denominator has decreased, but overall somehow this ratio has increased, okay, as you increase the value of alpha. And the reason why this is happening is because, remember, the quantity in the numerator is related to the power delivered to the load, and the quantity in the denominator is related to the power absorbed from the voltage source VDD. So, the net power delivered to the load as well as the net power drawn from the supply are decreasing. Okay. You will find that just one factor has cancelled out, there is nothing much in it. Okay. Both of those quantities are decreasing, that is being reflected by the fact that the height of this current waveform has decreased. When you are decreasing the conduction angle, you are making this current waveform smaller and smaller and smaller in size, right, the rest of it is all 0. Okay. Now, if that is your small I sub capital D, that is being delivered by VDD, the average of that is being delivered by VDD. So, the average current is also going down. So, it is not like you are going to give more than you take, the entire thing is going down in size. All right. In the limit, suppose you plug in alpha equal to pi by 2. So, in the limit alpha is equal to pi by 2. So, you say I am not going to conduct at all, or I am just going to conduct at this point, at this one point. Okay. What you are going to find? Let us try it out. If alpha is equal to pi by 2, how are you going to do it? You are going to plug in alpha equal to pi by 2. So, pi minus 2 times pi by 2 is 0, minus sine of pi is 0. So, your numerator has become a big 0. Your denominator is 2 times cos of pi by 2, cos of pi by 2 is a 0, minus pi times sine pi by 2. So, that is minus pi, plus 2 times pi by 2, which is pi times sine pi by 2. So, that is also 1. So, minus pi plus pi, which is 0. So, your numerator is 0, denominator is 0. Okay. So, you have got a 0 by 0 situation, and therefore, we have to take the limit alpha tends to pi by 2. All right. Instead of alpha tending to pi by 2, let us replace, let us call pi minus 2 alpha as some theta. Okay. just so that the maths is easy, and then I will do limit theta tends to 0. So, pi minus 2 alpha is theta minus sin 2 alpha. So, 2 alpha is pi minus theta, right. So, sin 2 alpha is sin of pi minus theta, sin pi minus theta is equal to sin of theta. Two times cos of alpha, 2 alpha is pi minus theta. So, alpha is pi minus theta by 2, or rather pi by 2 minus theta by 2. Okay. So, cos of pi by 2 minus theta by 2 is just sin of theta by 2. Minus pi times again sin alpha, which is going to be cos theta by 2. Two alpha is pi minus theta, okay. And in the denominator you see there is pi minus pi cos theta by 2 plus pi cos theta by 2. So, they cancel out, all right, and then you get okay. You can double check. If you plug in theta equal to 0, this is 0 0 0 0. So, you still have 0 by 0, and then we will do a limit. How do you do a limit when there is a 0 by 0? You take the derivative, right, of both numerator and denominator, your L'Hopital's rule. So, you take the derivative of the numerator, you get 1 minus cos theta divided by 2 times sin theta by 2 derivative is half cos theta by 2. And theta cos theta by 2, you have to break it up. Okay. And these cos theta by 2's cancel out. This by 2 also cancels out. And you again plug in theta equal to 0, and you see that you have still got a 0 by 0, which is still not good enough. So, you do the derivative again.
So 1 minus cos theta is 2 sin square.
Perfect. So, one possibility is instead of doing a derivative again, you suggest that 1 minus cos theta is equal to 2 times sin squared theta by 2. There is a half which has disappeared mysteriously. Okay. So, this sin theta by 2 cancels out. Yeah, it is fine. No, there was a theta here. Yeah, that is better. Okay, it is correct. We are still doing limit theta tends to 0, and then it is sin theta by 2 by theta by 2, which is equal to 1. So, what do you see over here? You see that as you are dropping the conduction angle all the way to 0, it is as if the efficiency is building up higher and higher and higher all the way to 1. Although in reality, as you are dropping the conduction angle to 0, you are not doing anything. You are barely supplying any current and barely pushing that current into the load. But whatever you are doing, it is very good, it is 100% efficient. Okay. So, this limiting case of the amplifier is called a class D amplifier. Okay, where your conduction angle drops all the way to 0. Now, what does that mean? That means that the MOSFET barely ever switches on, and when it does switch on, okay. So, this is our circuit. Okay. Now, consider the following situation. Consider this MOSFET to be a very good MOSFET, very large in size, and it is going to operate as a perfect switch. What does a switch do? A switch is either on or off. Okay. When the switch is on, these two voltages are equal. Therefore, the power consumed by the MOSFET when the switch is on is equal to 0, because these two voltages are equal. Okay. Power consumed by the MOSFET is the voltage times the current. Right. Power consumed by the MOSFET is V d times I d. When the switch is on, V d is equal to 0. The MOSFET does not get to consume any power. When the switch is off, I d is 0, because the switch is off, in which case again the MOSFET does not get to consume any power. So, if I can operate the MOSFET as a switch, then the MOSFET does not consume any power at all, which means whatever comes from the power supply makes its way to the load. The power that the power supply produces can only be delivered to the load, because nothing else consumes any power. Okay. So, this is the understanding, this is the class D amplifier. In the class D amplifier, what you are going to do is you are going to operate this MOSFET as a switch. You think nothing is going to happen over here, okay. You think you are not going to do anything, the MOSFET is not doing anything, but no, you are wrong. Wait a second. Okay. What you are going to do is this voltage what you are going to do is you are going to make sure that the signal is enough to switch the device either on or off, and the MOSFET is not going to behave like an amplifier at all. This device is so large, so great, and the input amplitude is so large, so strong, that the MOSFET is going to work like a switch. When it is on, immediately V d is going to become equal to 0. Okay. So, all the current will get delivered to the load. When it is off, I d is equal to 0, which means all the power will get delivered to the load. Okay. So, this is a classic class D amplifier. Class D amplifiers are very hard to make, right. The theoretical efficiency of the class D amplifier is 100%. However, in a lot of audio systems, we find that the class D amplifier is quite popular because of its efficiency. So, what you do is at the input over here, instead of applying the actual audio signal, right, the audio signal looks like this, something. Instead of applying this audio signal, you encode this audio signal as a pulse width modulated waveform. Okay, a very fast, this audio signal has a bandwidth of 20 kilohertz, maximum bandwidth, including music, right, high quality music. The human audio signal has a range of 20 kilohertz, some 20 hertz to 20 kilohertz. Okay. Now, what we do is instead of just a 20 kilohertz bandwidth, you say that let us take a 1 megahertz bandwidth, all right. And in this 1 megahertz bandwidth, you convert this 20 kilohertz signal into a pulse width modulated waveform. What is pulse width modulation? What is it? Here it is a square wave, where the width of the pulse is proportional to the signal amplitude. Okay, suppose the signal amplitude is this much, then I produce this. Suppose the signal amplitude is this much, I produce this, okay, this pulse, and these pulses are coming fast, right, much faster than the bandwidth of the signal. Okay. So, the bandwidth of this particular signal is much larger than the bandwidth of the original signal. The original signal is just 20 kilohertz, this one is very high bandwidth, okay, and it is a switching waveform. Now, we apply this switching waveform over here, right. The current, the MOSFET is switching on and off, this is a digital signal, all right. This is a pure digital signal, the MOSFET is just switching on off. When it is on, V d is 0, MOSFET does not consume any power, power is delivered to the load. When it is off, current is 0, once again power is delivered to the load. No matter what you do, power is delivered only to the load and nowhere else, all right. Applications such as the hearing aid dump, they do not even put the filter over here, lot of hearing aid applications, they do not even bother putting a filter over here. Why? Because they say that the human ear is a good enough filter, right. Anyway, the human ear has a range of 20 kilohertz, right. All the harmonics outside of 20 kilohertz, he is going to filter it out anyway, right. Of course, this leads to a lot of distortion, because if the signal was not 20 kilohertz, if the signal was 1 kilohertz, then all its harmonics are there, right, 3 kilohertz, 5 kilohertz, 2 kilohertz, all the harmonics are there if the signal is 1 kilohertz. But the hearing aid engineer says that okay, that guy, the patient was not able to hear anything, let him hear at least a distorted signal, it is okay, right. At this price, this is what I am going to give him, he eliminates the filter altogether. Okay. Then a lot of other applications, what they do is they say that the load is inductive. In an audio speaker, the loudspeaker, right, the speaker itself is an inductor. So, you form an LC filter over here right away, and you engineer the LC values such that you get the right filtering. Okay. This is also something that a lot of engineers do. So, they eliminate this filter altogether. Alright. So, this audio speaker can be modeled as an inductor in series with a resistor, right. It is not a pure resistor, in which case you have got L, C, R in series. Now, you play with the C value and you make sure that it is a nice filter and cuts out all the signals that you do not want. Okay. You could also remodel this as L in shunt with R, right. So, lot of possibilities are there. In fact, that would be a more natural model, right. L in shunt with R will be a more physical model than L in series with R. Anyway, so you play around with these values and you can actually, it is possible to eliminate the filter altogether. Hi-fi applications will actually put a filter over there, right. Let us say you have got a hi-fi, high fidelity audio application. Let us say you pay a lot of money and buy a nice stereo player, right. They are going to actually implement a real filter over there and make sure that the output sound is clean. However, a lot of these systems come like this. Okay. There are a few exceptions, the exceptions being car audio amplifiers. Okay. Car audio amplifiers that you use in the car, your radio, car radio speaker, right. There you do not use this, and the reason is that this generates a lot of harmonics, right. Things are very different in the car. There is a lot of electromagnetic emission inside the car, and that is going to create a lot of problems, right. You do not want, for example, this audio amplifier to start interfering with the engine control. Okay. So, a lot of critical things are there, and as a result, in applications like a car, you are going to stick to cleaner amplifiers, which are class A and class B at best, okay, not class D, because class D is known as a switching amplifier. All right. So, these power amplifiers can be classified into two broad classes. One class is the linear power amplifier, the other class is the switching power amplifier, okay, where the device is being used as a switch. So, the switching power amplifier is class D, the linear power amplifier, okay, this linear, take it with a pinch of salt, all right. The circuit is not a linear circuit as such. However, the amplitude of the signal varies with the amplitude of the output power. The output power changes with the input amplitude. Okay. So, these are called linear power amplifiers. A switching power amplifier is class D, and then there are a few more, they are called class E and class F. Okay. So, they are all variants of class D power amplifiers. We are not going to study them. Fine. Efficiency in class A is 50%, class B is 78%, theoretical maximum, class C is greater than 78%, class AB is between 50 and less than 78. These are the theoretical maximums, okay. And class D, E, F, they are all switching, their theoretical maximum is a cool 100%, okay. But then again, these are all theoretical maximums, you are never really going to hit these values. For example, if you start designing a class A amplifier, then you are never going to achieve 50%. Your supervisor, your boss will be happy if you hit 25. Okay. You start designing a class C amplifier, you are never going to hit 78%, you know, anything greater than 78%, it will be nice if you can manage 70%. You start designing a class class D, E, Fs are very hard to design, but you start designing them. Let us say you start designing a class E amplifier, right. Your target is 100%, but you will never reach anywhere close by. You will probably be somewhere around 75%, you should be happy. Okay. So, these are the different power amplifiers, right, and they are all, what is the circuit? The circuit is the same, this one, right, there is nothing different, it is the same circuit, you are just playing with the VGS value, and in case of the switching amplifiers, you change the input signal as well, you make it a pulse width modulated nice huge digital signal, right. You make the MOSFET big in case of a class D, E, F amplifier, right. But otherwise the basic circuit is the same. The idea is how to split up the current waveform, the voltage waveform, how to take out the fundamental, that is where everything is. Okay. Now, we are going to do one last power amplifier, and so let us think about this. So, let us say we are doing a class B power amplifier. We are trying to attempt a class B power amplifier, where the conduction angle is perfect 180 degrees. Okay. So, what does that mean? That means that when my input, so my VGS is probably exactly equal to VT, right, something like VT, such that when the input goes below VGS, this MOSFET does not conduct at all. When it goes above VGS, the MOSFET starts conducting. Okay. So, the shape of this current is this. Fine. What if I make one more amplifier? Okay. So, what if I make one more amplifier where the shape of the current is this? Is that possible? I can implement it easily with another class B PMOS amplifier. Okay. In case of the PMOS amplifier, what do I have to do? I have to make sure that this voltage, the bias voltage, is exactly VDD minus VT, such that when VGS, the input signal, goes up, this one blocks out everything, but when it goes down, it pushes current, or rather it draws current the other way, right. When it goes down, yeah. Okay. So, this is the current waveform. If this is equal to 0, the current is 0. If the signal is 0, there is no current. If the signal goes down, there is no current. sorry, if the signal goes up there is no current, but when the signal goes down, I am sorry, these arrows are all wrong. When the signal goes down, the current that is being pushed goes up. Fine. All of these references are 0. That is the current that is being pushed. All right, is this okay so far? So, the same signal is being applied to both of these transistors, both of these MOSFETs. So, let us redraw. So, here I am applying something like this, okay, and this current has a conduction angle of 180 degrees. The other current also has a conduction angle of 180 degrees. Fine. And then I hook them up. Okay. If I hook them up and make sure that the current drawn from VDD is a constant. Suppose the DC current, okay, if you hook them up, what is this other current? This one minus, yeah, this minus the other current, okay, and this particular current is therefore going to be, in this phase it tracks the first one, fine. So, what I am doing is I am calling this IDN, IDP, and ID is equal to IDN minus IDP. All right. And what I do is I am going to put this across my load. All right. When I do that, I get both of these MOSFETs are operating with a conduction angle of 180 degrees, pi. Pi is the conduction angle. Both of them are class B. Okay. Both of the MOSFETs are operating in class B. Is that okay? The resulting current is coming through the load. So, one PMOS is pushing current into the load, the other NMOS is pulling current out of the load. So, this kind of strategy is called a push pull class B power amplifier. The efficiency of this power amplifier is exactly the same as that of the original class B. All that you have done is you have replaced the inductor with the PMOS, right, and for the PMOS you have replaced the inductor with an NMOS. Okay. And then you have to organize these bias voltages. These bias voltages are critical. Okay. You have to organize this to be perfect such that the PMOS is class B. You have to organize this as perfect such that the NMOS is in class B. Once you have organized the bias voltages, everything is going to fall into place. Now, how you are going to do this is actually your own business. All right, it actually is your own business, right. One possibility would be that you somehow generate these, okay, somehow, and then couple the input signal in. Okay. You can do this through a resistive network, you can do it through other, but you have to be perfect. It has, this has to be something like VT, right. Maybe you can do it through another MOSFET, right, which emulates a VT voltage, right. This should emulate a PMOS VT voltage, right. You can do a number of things to do that. For example, you could have a current source which is drawing current from VDD, right, and it gives you a VT drop over here. So, this part is your business. As long as you do this part right, this is going to push, this is going to pull. You can even make this as common drain as opposed to common source. Actually, the common drain is also very popular. It is a very popular push pull class B power amplifier, where you put the NMOS on top and the PMOS at the bottom. I forgot to put the capacitor over here. Okay. So, here what you have to do? The NMOS has to be biased just right, so that when the voltage goes up, the NMOS works. When the voltage goes down, the NMOS does not, should not produce any current. Okay. And likewise, the PMOS is just the same. Right. This voltage should be such that it should be perfect, such that when the voltage goes up, the PMOS does not conduct, but when the voltage goes down, the PMOS draws current. So, in this case, the NMOS is pushing current, the PMOS is pulling current. So, this is also a push pull class B power amplifier. Okay. The classical ones, the classical push pull power amplifiers are made with BJTs, bipolar junction devices, and you will find them in the books. I encourage you to check them out. However, since we are not going to talk about BJTs, bipolar junction devices, in this course at all, I am not going to talk about those classical push pull class B power amplifiers with BJTs. Okay. With MOSFETs, you just have to organize these bias voltages right. BJTs also, the problem is the same, organizing those bias voltages. They do a lot of tricks to do that with BJTs, they use diodes and so on. In case of the MOSFETs, you can use similar tricks. You can imagine a resistive network like this, right, where this drop just has to be V t of the PMOS, this drop has to be perfectly V t of the NMOS. Okay. V t of the NMOS can be obtained by, you can obtain a V t of the NMOS by pushing a small current through a large N channel MOSFET. If I push a small current through a large N channel MOSFET, right, VGST required for this MOSFET is going to be very low, which means that this is just going to be enough, it is just going to be VT, right. So, for example, this bias network could be built in this fashion. You push a weak current through a large MOSFET, you get your VT. Okay. And then of course, you have to couple in the signal into this. Your input signal, and this goes to your input transistor, input NMOS. And likewise, a weak current, if you pull it through a large PMOS, you get a VT drop over here, right, and you can couple in your signal, and that goes to your input PMOS, and then you organize them as push pull, decouple the load, and there you are. Okay. So, these things can be done. All right. So, this more or less concludes our what is the efficiency of this? What is going to be the efficiency of this? 78%, not 50. 50 is class A, right. Here the NMOS is off for half of the time. While the NMOS is off, it is not consuming any power. Okay. So, during the second half cycle, only the PMOS is pushing power, the NMOS is off. During the first half cycle, only the NMOS is pushing power, the PMOS is off. All right. Overall, it is class B in the first half cycle, class B in the second half cycle. Overall, you get a class B performance of something close to 78%, pi by 4. Okay. So, this more or less concludes our discussion on power amplifiers. We have looked at them in quite some detail, right. We have not done enough to actually make real RF power amplifiers for cell phones, but we have done quite a bit, right. We have covered the basics of power amplifiers, both in terms of audio power amplifiers as well in terms of cell phone power amplifiers, which are going to drive an antenna. So, both of those we have covered, and next we are going to look at voltage regulators in the next class. Thank you.